Hey everybody, this is Mr. Ainsworth. Good morning to you. All right, we're going to get right into your homework problem number 3 and talk about how to solve a bacteria problem here. This one's entitled Bacteria Growth. So let's read it together here and see what's going on and see how this can be applied to, or exponentials can be applied to bacteria growth. So first of all, a scientist has discovered a new strain of bacteria. Ooh, sounds like a movie. The bacteria culture initially contained 1,000 bacteria, and the bacteria are doubling every half hour. So we got a couple important things going on. First of all, the initial mouth, okay, is 1,000 bacteria. That's A in our function right here. So initial amount, A sub I, equals 1,000 bacteria. Okay, ooh, bacteria here. Initial amount. All right, the question is, well, actually, the bacteria doubling. Ooh, doubling. Every half hour, that is your time interval here. So every half hour, every 30 minutes, all right, because you know that there are 30 minutes in a half an hour, the number of bacteria grows, all right? Now, in the beginning, we start off with 1,000, okay? So I'm going to actually insert that in the table. In the beginning, at time equals 0, we have 1,000 bacteria present. Okay, let's label this start. All right, so in the beginning, there are 1,000 bacteria. Every 30 minutes or every half hour, it doubles. All right, this right here is important. Okay, so let's fill out the table and check out what's going on. So after one time interval, one doubling or one time interval every half an hour or 30 minutes, you double. So right here, 1,000, well, obviously times 2, you get, ooh, we got sound effects in the background. That is cool, man. You get 2,000 bacteria because 1,000 times 2 is 2,000. Well, every 30 minutes, it doubles again. So after half an hour, 30 minutes later is an hour. The second time interval, all right, it doubles. So you got to multiply by 2 again, right? And so what do we have? We have 2 times 2,000. Ooh, 4,000. Okay. Now on the calculator, if you want to do this, all right, just have it off to the side, clear it out. You start off with 1,000 bacteria. So if you're weak on multiplication, no big deal. This is here for you here. So we got 1,000 times 2 equals 2,000 times 2 equals 4,000 times 2 equals 8,000. And after you do it 3 times, the calculator remembers a pattern and doubles it for you. All you have to do is press the enter button. See, look at that. It doubled 8,000 to 16,000. So every time you have there's another time interval, or every doubling, it doubles. So times 2 again, all right, it doubles. 8,000 bacteria present after an hour and a half, after 3 intervals. Half an hour, half an hour, half an hour, that's 1.5 hours. Or 30 minutes, 60 minutes, 90 minutes, if you want to do it in minutes. Okay, you double it again, times it by 2. 16,000 bacteria now after 2 hours, which is just 4 doubling intervals, okay? After every interval, again, let's highlight this. These are the intervals. After each interval, which is 30 minutes or half an hour, it doubles, all right? So times 2 again, okay? No big deal. So if you can't do it in your head because you're weak on multiplication, no big deal. Learn how to use your technology, right? Hit the enter button because it remembers the pattern. It doubles it for you after 3 times. You have 32,000 here. So 32,000 bacteria. That's getting to be a lot, by the way. That's after 2.5 hours or 5 intervals. Again, these right here are the number of intervals where it's doubling right here that I'm highlighting. This is going to be our x values here in a minute here. X is going to be the number of time intervals. And the bacteria present is going to be y in our function here. Okay, so what's 32,000 times 2? All right, if you know how to double in your head, multiply by 2, that's 64,000. But like I said, you can let the calculator do the work, double it again, you get 64,000, double that, 128,000. So again, just pump out the arithmetic here, you get 128,000 here, write small. That's after 3.5 hours. That's it, man. After 3.5 hours, that's a very short period of time. You already have 128,000 bacteria. And that's why bacteria is so powerful. It could be good and bad, by the way, because there's good bacteria and bad bacteria. But if it's bad, you got a problem. All right, you double again. All right, 128,000 times 2, that's 256,000. So 256,000 bacteria after 4 hours or 8 intervals. Okay, every interval it doubles. And then times it by 2 again. Well, what do you get? You double 256, you get 512. So it sounds like 512,000, which it is. How about that? So 512,000 here, bacteria. You double it again after 5 hours. That's a very short period of time. You have 1,024,000 bacteria. So 1,024,000 bacteria after only 5 hours. And that is amazing. Okay, so what in the world is the pattern here? We've got to write a function to illustrate this, but let's take a look at some patterns here first. All right, so the 2,000 here, let me see, it's 1,000 times 2. Okay, so let's write this down. 1,000, we got that by 1,000 times 2, which is the same thing as 2, the first, by the way. To get from 1,000 to 4,000, what do? Well, you can see 1,000 times 2 times 2. Well, that's 1,000, the initial amount, times 2 times 2, which is 2 squared. To get from 1,000 to 8,000, well, you take 1,000 times 2 times 2 times 2. So you take 1,000 times 2 times 2 times 2. Well, that's 2 cubed. Why? Because there's 1, 2, 3 of them. To get from 1,000 to 16,000, you got to take 1,000, which is your initial amount, times 2 times 2 times 2 times 2 4 times, but that's the same thing as 2 to the 4th. Do you see a pattern here? I mean, take a look at this right here. See, 1, 1, 2, 2, 3, 3, 4, 4. Ooh, there's a pattern here. To get from 1,000 to 32,000, you got to take 1,000 times what? 2 times 2 times 2 times 2 times 2. That's 2 to the 5th, or 32. Oh, I didn't mean to write that. 2 to the 5th. Well, you could put 32 there, but that's actually, well, that's 2 to the 5th. All right, to get from 1,000 to 64,000, you multiply by 64, but that's 2 to the 6th. All right, so 1,000 times 2 to the 6th. Once again, look at the pattern here. After the 5th interval, time interval, that's 5. After the 6th time interval, that's the exponent 6. It's the same, and this gives us our function here, by the way, our pattern. So you got to be trained in looking at patterns. So from 1,000 to 128,000, well, that's 100,000 times 128, but we know that it's 2 times 2 times 2 times 2 times 2 times 2, and that's 2 to the 7th. All right. Ooh, look at that. It corresponds with a time interval. Look at that. All right, so I already know what this is. This is going to be 1,000 times 2 to the 8th. This is going to be 1,000 times 2 to the 9th, and this is going to be 1,000 times 2 to the 10th. Once again, look at the time interval and look at the exponent. Look at the time interval and look at the exponent. All right, and we already know that a sub I is the initial amount, so this is the initial amount right here, base 2, all right, because we're doubling here. It's a growth function, and this is the time interval, which we're going to call x in a minute. So this is going to be a times 2 to the x power. So I already know that the y, which stands for the number of bacteria, is going to be equal to a, the initial amount, all right, times 2 to the x power, or in general, 1,000 times 2 times, okay, put a dot there, times 2 to the x power. Now, if you remember from before, we had a general growth function. Let me just write this over here. Go to the margin with me. In fact, let me go refresh your memory. Let me go back 3 or 4 lessons here. I talked to you in the past about, let's see here. Ooh, that's it right there. That the growth functions is always the future amount here, a sub f, is equal to the initial amount, a sub I, times 1 plus r, where r stands for, look right here, growth rate, to the t power, where t is the number of time intervals. Okay, so let's go back to our lesson here and let's write that down. Always use your notes to your advantage, okay? Meaning that you look at them in the past and use them in the present. So we have y equals here a times the quantity 1 plus r to the t power, time intervals. So in this case right here, the growth rate doubles. So R is 100%. Right here, R, if it doubles, you grow by 100%, which is equal to 1. Well, 100 divided by 100, which is equal to 1. So R is equal to 1. So if you put in here, in this function here, the initial amount right here, the initial amount right there, you get y is equal to 1,000 times 1 plus 1. Got to substitute in the growth rate. I mean, because if it doubles, then it increases by 100%, right? To the, not t power, but in this case, the time intervals is x now, so to the x power. What does that give you? It gives you y is equal to 1,000 times 2 to the x power. Notice these are the same. All right, so our function is y equals 1,000 times 2 to the x. It's a growth function. All right, why? Because things are doubling. Okay? So what we need to do now is we need to plot the data and see what's going on. So let's go ahead and do that, but we're obviously going to have to adjust the axis here, the y-axis, because we got to go from 1,000 to 1,000,000 roughly. So we'll only plot the first few just to get an idea. Let's go to adjust it to, I don't know, let's see here. This is the number of time intervals here, so x time intervals, not the number of minutes, okay? I'm talking about time intervals. How many intervals that it doubles. And this is right here, the number of bacteria that are present. So instead of counting by ones, obviously we have to count by 1,000. So this is 1, 2. Actually, you know what we're going to do? We're going to go times, well, this is 2,000 here. All right, 4,000. So we're counting by 1,000s here. 6,000, 8,000, 10,000, 12,000. Okay, 14, 16,000. You get the idea. 18,000. All right, 20,000, because we're counting by thousands. So now we can graph a couple points and see what this growth curve looks like. And remember, x-axis is not time in minutes, it's number of intervals, time intervals. So we're going to graph 0, 1,000 as our first point. Let me decrease this so you can see things a little better here. Okay, there we go. So I'm going to put it in blue so you can see it. No, in red. So 0, 1,000 right here. There's your y-intercept. 1, 2,000. So 1, 2,000 is right here. 3, 8,000. So 3, 8,000. See, look at that. Just take it off, right? And then 4, 16,000. So 4, 16,000 right here. And then 5, 32,000. Well, it's off the graph. Okay, so you can already tell that this growth curve increases exponentially. So growth increases exponentially, and that's what we mean by really, really fast. Okay, and that's what you got to get used to. That's the new terminology. That is amazing. Okay. Now, from your graph, determine how many bacteria are present after 45 minutes. Okay, well that's not in the table, is it? Because we got data on 1/2 hour, which is 30 minutes, and we got 60 minutes. Now, if this is, let me increase this so we can go back so you can see things better again. We know that 45 minutes is right in between, it's right in the middle here. If this is 30 minutes and this is 60 minutes, then 45 minutes is in the middle. So, you know, what would that be? Well, how many time intervals is that? It's not one interval, it's not the second interval, it's right in the middle of the first and the second. So how about 1.5 time intervals? So after 45 minutes, it kind of looks like 45 minutes is 1.5 time intervals. But so if this is, it's between the first, let me see, on the graph. So between 1 and 2, it's between 1 and 2, so 1.5. So let's try to use a graph here. Here's 1, and this is obviously 2, so here's 1.5. There's, after 1.5 intervals, this is 1.5 intervals, 1.5 basically. Okay, that's basically what I'm saying. So what you do is you go up to the graph, and you go across, and you read the value there. And then you figure out, how many bacteria are present. So it's between 3,000 and 4,000. So it's a little over 3,000 bacteria. That's on the graph. So if I was going to estimate, I would say about, okay, maybe 3,100 or a little over 3,000. So we'll estimate 3,100 bacteria. All right, from the graph. But you can do better than that. All right, we know the function. So if you know that it's y equals 1,000 times 2 to the x power, then you enter in 1.5 up here, and let's see what we get. So what's y equals when we have 1,000 times 2 to the 1.5? Well, let's figure that out. 1,000, all right, times 2 raised to the power of 1.5. All right, maybe let's use parentheses here. I'm not sure if we need them or not, so let's use them just in case. 1.5, there we go. And we have about 2,828 bacteria, which is close to our estimate. All right, so this one here, 28, let me just record this here. Here we go. Let me bring in the calculator. This is what's cool about this technology, man, is that we can just do this right here. Let me clean this up a little bit. There we go. Boom. All right, so we have that from the calculator and we have about 2,828, so y equals 2,828 bacteria, all right, after 45 minutes. So let's record that after 45 minutes. Pretty cool. So I did it using the function right here, but I also did it by using the graph, and there's my approximate. All right, and I also got a better indication what I have after using the function. Okay. All right. So this is a video. Remember this, and your job is to learn it. So go back if I went too fast and redo it, and re-listen to it, and go through it yourself, and see if you can try to understand it. And I'll see you in my next video in homework problem number 4. I'll see you then.